Mm, okay. Looks like we're done. I mean, live. Okay. So, we left off at this part over here. So now we're at session 3, which is the last part of this. I don't know, they don't use like chapters or like stuff. They use like session and articles or whatever. Trying to be new and fancy. But after this is done, we're gonna head into a new section and hopefully it'll be more new stuff. Because this is honestly a bit boring. It's basically functions, it's stuff that most people know and understand already. So that's why we've been breezing through this pretty quickly, but I feel like a recap is still necessary. Let's look at some of the exercises from Article 1. Let me just see if okay, stream is doing well. Starting with exercises 2 and 3. Can you explain why the results HGF and HGF always come out the same? What can you say about the 4 maps in a row like these? Also, by the way, this is the last day of holiday for me, so school's starting tomorrow. I'll know how that's gonna affect the frequency of the stream, but we'll find out soon enough. But for now, we were streaming, and I started early today, so the idea is maybe we can do 2 streams today. One this, one something else. I don't know if it's gonna be another gaming or more studying. Clarification of these questions is what I was aiming at with the story of my mother and the tasks of scraping, washing, rinsing, and drying the dishes. The tasks were meant as an analog of maps so that the 4-step task corresponds to the composite map. When we first explained the composition of maps, we said that the basic thing is to compose 2 maps, for example those in the diagram. This diagram, as we said in last session, can itself be regarded as a rule to calculate the composite map G of F, namely the rule look at this diagram and follow the arrows. The internal diagram of GF looks like that. It's just a simplified rule to calculate the same map. If we do the same thing with H and K, we can pass by steps from what? The sentence cut off. Wait, if we do the same thing with H and K, we can pass by steps from... Yeah, that's definitely an incomplete sentence. But I think that this entire part over here is not important to understand. I barely even understand what I'm reading. The point is, he's just reclarifying and re-elaborating like the composition of maps, which we should all already have an intuition of how they work. Right? We can look at this diagram, and from this diagram, we can construct the composite map just by following the arrows. And we can do the same thing with H and K. Right? And then we get HK. So no matter if we do, GF first or HK first, like you could, I don't know how to say this, like you could do GF and then you could do HK separately, and then after you compose G and F together and compose H and K together, you can compose FG with HK, and you could get this 4 thing, but you could do it like here, and then you could group them in different ways, but it'll still be the same. It should still be the same. Yeah, that's what I was saying. You could group like these 2 together. So you do this one first and then this one next. and then you get G of F, and then K of H, and then you could repeat the same process again. First, you combine G and F together, you compose them together, then you compose H and K together, and then you compose those results again. So you're doing, another layer of composition with the already composed functions. And then you get this. But then if you can certainly do it in a different way. This is grouping K and H and G and F together, but you can group them in different ways, but the process will still be the same. And we have an intuition for this already, We could do it like one by one, and since this is saying that the grouping doesn't matter because like we're just following the arrows anyway from start to finish, right? Obviously the order of these sets, not sets, yeah, but the order of the functions does matter because then that would change the path. But whether you look at groups individually or not does not matter because the underlying path is always going to be the same still. Now let's see if we can find a way to tell the number of maps between any two finite sets. For that, we should start by working out simple cases. We sort of figured this out already. We had the formula, right? Like, Jesus, I forgot. It's yeah, the 2 to the power of 3, 3 to the power of 3, 3 to the power of 2, 2 to the power of 2, right? Yeah, so it's right side because the codomain is usually on the right side set to the power of left side set. And discover the reason behind it, which I sort of explained already. What's this? N1110 and not equal 0. Alright, hold on, let me read this. That's a very good idea. One has to discover the reason behind it. Let's see if it also works with the extreme cases that we found at the end of last session, which we sort of did as well. Where n is any natural number with the only exception that in the last column it must be different from 0. Now you should think of some reason that justifies this pattern. Wait, what? Oh, number of... Oh, this is... Just join the two tables, man. This is confusing me. So, if the domain is n and the codomain is 1, then there's only one mapping. So those are the examples that we did from last stream. And if there's one mapping and n number of codomains, then there's n maps. And if there's 0 and n, then that's 1. Yeah, if you're mapping nothing, then that still counts as a mapping for the reasons that I explained previously. And for n not equal to 0, otherwise you get 0 to the power of 0. Then, this case is shown here. And then you get that, okay? I mean, we've already... I think we can just skip this, honestly. Because we already know... I already explained this part. Right, it's just, we use this terminology to denote the number of elements inside a set. So, yeah, P and R are different sets, obviously, because they contain different things, but they contain the same number of elements. So we say the number of elements in P is the same as the number of elements in R. Oh, this is what we did as well. I remember doing this. Oh, this is an identity map because it maps the same object to the same objects. It maps it maps objects to itself. So obviously, if you compose an identity with an identity, you go from the same point to the same point to the same point again. So obviously, identity composed with identity is equal to identity itself, which is what this formula shows. So for any map from the set A to B and any map from set B to C, 1B composed with F equals F and G composed with 1B equals to G. So let's just see that. Do they have a diagram here? Nope. Okay, so I'll just show that in case people would want to see. Hold on. A, B, and then B, C, and then F, G. So you have A, B, C, this is F, this is G. And then we have the identity map 1B, which basically just loops around like this. This is 1B. I don't know. A lot of people use IB. I don't know why this guy uses 1B. So that trips me up a bit. I'm just gonna follow the book. So it's saying that, so when we're composing, I hope you catch this on already, it's read basically from right to left. So we do the right thing first, then we do the left thing next. So we follow F's arrow, and then we continue with 1B's arrow. So we follow F's arrow, and then continue with 1B arrow. So 1B composed with F is equal to F, because this, we follow this path, and then we do this path. So that's the same thing there. Right, and we know that because the identity function maps the same points to the same points. So it basically has no effect. And of course over here, it's different because now you do 1B first, and then you do G. So you do 1B first, and then G, and then that is equal to G. Right? There could be other functions that map from B to B, but that are not the identity. Maybe we'll call it A, not just because there's A already there. We'll call it Z. So we could have, this is B, say for example, and we could have Z. This is the function Z, or the map Z. It doesn't map the same points to the same points. So if you have, say, the set A with a bunch of arrows like this, then obviously composing, so we do F first, then Z, and this will not be equal to F, because A maps this point to this point, this point to this point, right? That's the mapping of F. But then you do Z afterwards, and then you go down and then up. That's an extra step that you use. So ZF is then You follow the arrow here and then down, here and then down. You follow the arrow here and then up, here and then up. Right, that's ZF. Whereas F maps the top element to the top element, the bottom element to the bottom element. This does something different, so they're not the same. However, with the identity function, it maps the same points to the same points, and the same points to the same points. So the instructions from F are not modified by this extra step, right? We do F first, and then we do the extra step of, composing it with Z. We have to follow another arrow, follow this arrow, and then follow this arrow. However, if the arrow that we follow next in the next part essentially just brings the same point to the same point all over again, then that will not have an effect towards, what F is trying to do. This messes up what F is trying to do because it swaps things around, but if everything remains the same, then there will be no overall effect, and the functions will remain the same. They'll remain unaffected. So hopefully that clarifies a few things. So yeah, these properties of the identity maps are like the property of the number 1, that multiplied by any number gives the same number. So identity maps behave for composition as the number 1 does for multiplication. That is the reason 1 is used to denote identity maps. Okay, that makes more sense now, the notation. What's another map, G, from xcoffee to xcoffee that satisfies G composed with G equals G? What about the map, this guy? I think this was one of the examples that I used as well. So if you repeat the map again, this is G, you follow the arrows, eggs goes to eggs goes to eggs, so eggs goes to eggs, that's the composition of the arrow. Coffee goes to eggs, so coffee ultimately ends up being in eggs, so coffee ultimately ends up being in eggs. So the composition is same as the original function. So we did the exercises already, so we can just skim through this. One suggestion is to look back and use the special diagrams available only for endomaps explained in Article 1. When did you talk about endomaps? What the hell is an endomap? Did I miss it somehow? Go up. Oh, what's an endomap? A map in which domain and codomain are the same object is called an endomap. Ah, so that's what it means. A map in which codomain and domain is the same. Alright. Here are some exercises on the bookkeeping rules about domain and codomain of composites. Hey, it's just 2 exercises. And we reached part 2, so that was quick. Let's also do part 2 then, since we have the time. A, B, and C are 3 different sets, or even 3 different objects in any category. F, G, H, and K are maps with domains and codomains as follows. 2 of the expressions below make sense. Find each of the 2 and say what its domain and codomain are. Right, so some of these don't make sense. So let's see which ones there are. So let's just turn all of these into one single diagram. We have A, B, C, and D. We have F, G, H, wait, what? A, B, B, A. Ah, Jesus. A, B, B, A, A, C, C, B. A, C, C, B, H, K. So we read from right to left, so we do F, G, H, then K. Let's see if that makes sense. We do F, and then G, and then H, and then K. That makes sense, right? So we started with A, F, G, H, K, and we ended up at B. So the domain of the composition, overall, we're ultimately sending elements of A to elements of B. So the domain and codomain of A is from A to B. Let's take a look at B. G, F, K. So G, F, and then K. Right. So that does not make sense because K sends elements of C to elements of B. Right? We do G, we do F, and then the arrow is left at, elements of B. So we have arrows pointing to elements of B. And then we're only given the information of arrows that point from C to B. Right? This is C, and then it points to B. Right? There's no way to continue the path. Right? We went from G to F, G to F. Right? Just maybe let's make this better. So B goes back around. This is FG. And then we have K there. So we have arrows which point from elements of B to itself. But then we can't continue the path because these arrows point from C to B, not from B to C. Right? So there's the composition, there's no way to complete the composition. It's not valid. So B is a no-go. C, we go from H, K, G, F, G. H, K, G, F, G. That makes sense. And it goes from A to A. So H, we started at A. K, G, F, G. We landed back at A again. Right. Do exercise 1 again. First, drawing this diagram. Wow, I did it already. Nice. Now just read each expression from right to left. Well, that's exactly what we did. Jesus. Oh my god. I'm one step ahead. I'm just that good. I'm unstoppable. Yeah. We investigate the analogy. If composition of maps is like multiplication of numbers, what is like division of numbers? The answers shed light on a great variety of problems, including in session 10 continuous problems. Okay. Isomorphisms. It seems probable that before man learned to count, it was first necessary to notice that sometimes one collection of things has a certain kind of resemblance to another collection. For example, these two collections, mother, father, child, feather, stone, flower, are similar. In what way? Remember that numbers had not yet been invented, so it's not fair to say the resemblance is that each has 3 elements. How are they similar? Jeez, yeah, I don't know. So explain to us. After some thought, you may arrive at the conclusion that the resemblance is actually given by choosing a map. For instance, this one. What special properties does this map F have? We would like them to be expressed entirely in terms of composition of maps, so that we can later use the same idea in other categories, as well as in the category of finite sets. Properties should exclude maps like these. The crucial property that F has and the other two maps do not have is that there is an inverse map G for the map F. So we're talking about inverse maps now. I need to get water because I'm running out. Okay. Alright. So, inverse maps. I know a bit about those. So, if you have a set A and B, and you have a function or a mapping between these two sets, let's say it sends this guy to this guy, this guy to this guy, and this guy to this guy. Actually, let's not make it symmetrical, because then, like, I think the inverse map will also be symmetrical. It'll also look exactly the same, so let me just think up a better example. Yeah, let's do something like this. Okay, so we have a function. Sometimes we can create the inverse function, usually denoted like this. Now the inverse function will have the domain and codomain swapped. So if the function f sends from A to B, that's the domain, this is the codomain, then the inverse function will have the inverse function is a function with the domain and the codomain of the original function swapped around. So instead of having the domain A, it will have the domain B, and instead of having the codomain B, it'll have the codomain A. Right, but this is not a function just yet, right? Because a function requires instructions on how to map the elements of the domain to elements of the codomain. So how is this map constructed? Well, what we do is we follow the arrows around backwards, right? So if I have a function f that sends arrows from A to B, I want to make a map that sends arrows from B to A. How will I know which elements of B get sent to which elements of A? Well, let's just follow the arrow backwards. So we have the first element of B here. How will we know which elements, how will we know where this point gets sent to? Well, let's follow the arrow backwards. Okay, we follow the arrow backwards, we go down here. Okay, so the first element of B goes to the third element of A. Okay, so let's do that. First element of B goes to the third element of A. Okay, second element of B goes to the first element of A. Second element of B goes to first element of A. And the third element of B goes to the middle element of A. So this is what the inverse function will look like. Okay? So that's how we construct the inverse function. If someone gives you a function, then you can try or attempt to construct the inverse function for that, right? Just by following the steps that I did. Now, the problem is this does not always work. Like they say, for example, we have examples like this and like this, which don't make things work. So for example, we have 3 objects and then 2 objects. These map here and here, and this maps here. Okay, so let's do the inverse map then. So we'll have the domain and codomain swapped. First element, see the problem now, there's 2 arrows. So there's 2 paths that we can go, backwards from. Okay, we could potentially have this path here that goes to the first element and another path that goes to the second element. So the first element of set B can go either here or here. The second element of B goes fall backward to the third element of A. However, this is not a function. Like I said, a function maps one point of the domain into one point of the codomain. Okay, a function can't map one point to 2 different points. I think I mentioned this before. If not, then I should have. But I'm pretty sure the book wouldn't leave it out, and I basically just read every part of the book, so I should have mentioned that at some point. Right, this is not a function. So f is a function, right? But if we try to attempt to construct the inverse function of that, then that fails. Okay, another example in which this can fail is if some element of the codomain is left out. Right, and you can see the problem here. If we want to construct the inverse function, then how will we know where flower maps to? There's no backward path that we can follow. And so the inverse function will only have the necessary information. It only knows where to send feather, it only knows where to send stone, because they have backward paths, but it doesn't know where to send flower. So this function fails to be a function because it didn't succeed in mapping all the elements of the domain to the codomain. It missed out this third final element. Right. So that's the idea of the inverse function. Another cool thing about the inverse function is that it satisfies these formulas. So if we try to compose them, then you'll see. So if we compose f inverse with f, this is what we'll get. B gets mapped to the bottom, and then we go from the bottom back to the top. So in essence, we go here down, and then down, up again. So the first element of B ends up going back to the first element of B. Okay, what about the second element of B? Second element of B goes up, and then up, goes back down to the middle. Middle element ends up being the middle element again. Third element goes to the middle, middle goes down again. So down element goes to the down element here. So all the elements get mapped to exactly where they were. And what kind of mapping is that? Well, it's called the identity mapping, right? And similarly, if we do f and then f inverse, right? If we follow A to B and then B to A, wait, hold on. Yeah. A to B to the middle and then middle back up to the top again. Then it'll map the elements of A to the same elements of A again. Right? So depending on the order in which you do things, we could do F inverse and then F, or F and then F inverse. It'll be the identity map of either A or B. Right? If we do F first and then the inverse, right, then we're mapping from A going to B and then B going back to A again. So that'll be the identity map on A. Whereas doing things the other way around will create an identity map on B. So we say that a map is an isomorphism if the inverse of it is also a map, it succeeds in becoming a map, then we call it an isomorphism. So I guess that's what it means. Two objects are said to be isomorphic if there is at least one isomorphism. Right, there are also other isomorphisms. Right, so if we take the inverse of this, that also succeeds in becoming an inverse. One had to see that the notion of isomorphic or equinumerous or same size or whatever it was called has certain properties. A is isomorphic to A. If A is isomorphic to B, then B is isomorphic to A. If A is isomorphic to B and B is isomorphic to C, then A is isomorphic to C. Surprisingly, all these properties come directly from the associative identity laws for composition of maps. So that's our first exercise. Let's try to do it. Let's stop. Where do we want to stop? Let's stop at exercise 2. Alright. Show that a 1A is an isomorphism, right? So we're saying that this needs to have an inverse map. If there is a map B to A, for which G composed with F is the identity on A and F composed with G is the identity on B, right? So to show that this is an isomorphism, we need to show that there is a map since A and B are the same. So we need to show there is a map G and G composed with 1A is equal to 1A and the other way around. So 1A composed with G is equal to 1B, but A and B are the same, so it's just 1A again. Right, so we need to show that there is a map for which this is true. Is there such a map? Well, sure, G is equal to 1A is a map. Because if you substitute that in, first just notice that 1A does have domain A and codomain A because, well, it's just the top thing over here. So if you substitute this in here and substitute this in here, then obviously you know that this is correct and this is correct. So there is a map G which satisfies these conditions, right? I have shown you that there is such a map. Therefore, 1A is indeed an isomorphism. Find an inverse for 1A. So the inverse of 1A is actually itself, right? If you have 1A, maps here to here, here to here, here to here, you do the reverse, right? Follow it back around. First element goes to the first element, second element goes to the second element, third element goes to the third element. You're just essentially going to obtain 1A again because it maps the same points to the same points. So the inverse of 1A is 1A. So knowing this, it means that A is isomorphic to A because there is an isomorphism. If there's at least one isomorphism, then these two objects are indeed isomorphic. So that's the reflexive property down. Okay. A to B. F. F is isomorphic. Okay. And B to A, G is an inverse for F. Then G is also an isomorphism. Okay. So, number one, G goes from B to A. Right. These are the informations that we have that we can use. Okay. So for example, and this is our workspace. So for example, this I just got from here, right? I just used like one part of the diagram. I represented one part of the diagram. So how do we show that something is an isomorphism? Well, then we need to show that there is a map that goes from A to B. Let's call it Z. And we need to have ZG is 1A and GZ is 1B. Right? So there needs to be a map such that these equations hold true. Right. So we know that G is F inverse, so we can just write that in. Actually, we'll just write that in the formula. Alright. Now we need to find a mapping from A to B that satisfies these properties. And it's pretty easy. It's just Z is equal to F. Right, they're asking us, if there is a mapping from A to B that satisfies these properties, then you're good to go. This function G is an isomorphism. If you can show me a function from A to B that satisfies these properties, and we say, well, hey, F is that function that you're looking for, right? So what happens if we put F here and F here? Well, then we know that a function, when you compose with the inverse, gives back, the identity again. That's something we've gone through already. So F inverse, which is just G, wait a minute. Did I do something wrong? Oh yeah, I forgot to read from right to left. So if reading from right to left, this should be yeah. So this is same as G, this is same as G. So if you look back at the definition, then it's like, so F is like the one that we want to check if it's isomorphic or not. So we have G of F, and G is the function that we're looking for, right? So if we have Z and then the function that we want to check, then it's, wait, what? Hold on. Oh, because G is from B to A. Yeah, this is gonna be a bit hard to explain, but yeah. Okay. Z is F, and we substitute that in here and in here. The equations will be satisfied. We have F inverse, which is G, goes from B to A, and then you add F, which is Z. So A goes back to B, so it's the identity on B. Similarly, this is the identity on A. So I guess that's number 2 done. That's the symmetric property. Show that if A, B, B, C are isomorphisms, then F, K composed with F is also an isomorphism. Right. This is going to be a bit tough. Right, so we know that F is an isomorphism. And by definition, that means that there exists a function that goes from B to A that satisfies certain properties. Of course, we know that this is the inverse function. And K, we know, is an isomorphism, which means that there is a function which goes from C to B that satisfies certain properties that makes it so that we can call it the inverse. Right. Now we want to show that the mapping K composed with F is an isomorphism. How do we show that? We show that by providing a function which goes from C back to A that satisfies certain properties. So we need Kf and this certain function Z to be 1A, and we need Z, this certain function that we're trying to find, Kf to be the identity map on C. Right, so we need Kf, we need a function that goes from C back to A that just does nothing. So it cycles back around and does nothing, and then similarly we have the other one as well. Wait, oh my god, I did the same mistake again. Read from right to left, god damn it. So this is 1C, this is 1A. Right, we do Z first and then Kf. So Z is the function that we're looking for that goes from C to A, and then Kf. So that is just a mapping from C to C that we're looking for when composed together, and we need it to satisfy becoming the identity mapping. Yeah. And we do Kf first, and then we do Z, which is the map that we're looking for that goes from C to A, and we want to make it so that it's the result of the composition is the identity mapping on A. So what is this Z? Well, look at the diagram over here. How can we construct a mapping from C to A based on the information that we already have? Well, we have an arrow that goes from C to B and an arrow that goes from B to A. What if we compose these arrows together? Then we'll get the mapping from C to A, and maybe that will work as the Z that we're trying to look for. So let's do that. How do we compose this? Well, we do C to B first, so we do K inverse. And then it's from right to left. Remember, right to left. So it's this. Right? This is a mapping from the C to A. And let's see how this works out. Z is, what is it? F inverse K. And we have F inverse K. This is just substituting Z with K inverse. Right? Yeah, K inverse. Let's see if this is true. Well, first, we know that we can get rid of the brackets, right? It doesn't matter how you group things together, right? In fact, we can do any grouping that we want and it will not change anything. So I can group it this way, for example, and this way. Right, what is f of f inverse? So f goes here, and then f inverse goes back. So it's a mapping from A to A, and we know that it's going to be the identity. Right, so I can just replace this with the identity on A. And K inverse K. K inverse K. So that goes from C to C. This is 1C. Okay. Wait a minute. Did I do something wrong again? Oh god, hmm. Wait, this is F and then F inverse. Oh my god, of course. I read it from left to right. Idiot. And this is K inverse. It's K. Oh my god. Make such stupid mistakes. So, reading from right to left. F inverse F is the identity on B. Reading from right to left, we do K and then K inverse. K and then K inverse is also going to be the identity on B. Alright. Next step. We need to use something we learned back before. This thing over here. Wait, no. Wait, it's from the previous chapter. Jesus. God damn it. Go back. This guy over here, right? This thing over here. Right? If you have A, B, and then B, C. Hold on. Yeah, so we have 1B, F equals F. And look what they have over here, 1BF. Right? We can get rid of the brackets here. and we can group this together, and we can group this together. So we have 1b f equals f. Let's just verify that again. 1b goes here, like that. And we're doing f first, so a goes to b, that's f, and then b goes back to itself. So f and then 1b is just the same as f. Okay, let's do k1b next. So that's 1b and then k, 1b and then k. So that's the same thing as k. 1b and then k. Right, 1b and then k. That's just the same thing as k. So get rid of the brackets. Now we have f inverse f, k and k inverse. Right to left, so k inverse and then k inverse and then k. So we go from C back to C. So that's the identity on C. We do f and then f inverse, f and then f inverse. We go from A back to A again. That's the identity on A. Whew. We're done. Okay, so we show that it's reflexive, symmetric, and also transitive. Perhaps you will be partially persuaded that the effort is worthwhile if we look at an example from geometry. Due to Descartes, P is the plane from geometry that extends infinitely in all directions. R squared is the set of all lists of two real numbers, positive or negative, infinite decimals like square root of 3 or negative pi or 2.1397. Descartes' analytic approach to geometry begins with an isomorphism that goes from plane into R squared. The plane is, their usual xy plane. And there's an isomorphism between this and R squared. So R squared is basically the set of ordered pairs of any two real numbers. So like 5, 10, 10, 5, just basically the first spot can be any real number, the second spot can be any real number. And you just put that into a set. Right, so it'll be the set of all pairs of real numbers. There is an isomorphism between this guy and this guy over here. And obviously it's clear, right? I pick any point on the plane here. I can turn that into a number. There's a mapping from here into here. So this point, how do I instruct, how do I know how to send this point on the plane into a pair of real numbers? Well, I measure the distance from the origin into sort of the shadow that this point casts. So I measure the distance between the origin and the shadow that this point casts, and let's say that's 5. Okay. And next what I'll do is I'll take the height of this point, right? And I'll measure the height of this point. I'll take a ruler and I'll measure the height. Maybe that's also 5. So with that information, I can make the mapping so that this point gets sent into the coordinate 5, 5. So the first coordinate will be the horizontal length over here, and the second point will be the vertical length, right? And I can do that for any other point as well. I could pick this point, I could pick this point. So if it's here, then the length will be negative. And if it's here, the length will also be negative on this other side, right? So then this point will say get it mapped into -5, -5. And it's an isomorphism because essentially we can do the reverse, right? If you give me a number 1010 from r squared, I can convert that back into the plane. I can send that back into the plane. How am I going to do it? Well, I'm going to measure a distance of 10 from the origin, or horizontal line, 10, and then I'm going to go up by 10 as well. And then that's going to be the point, right? 1010 gets mapped to this point, right? This is the domain, this is the codomain. There are instructions that allow us to map points on the domain into the codomain. And then we can flip things around as well. We can, we also have the instructions to map this point back into the plane as well. And the mapping that we just described is reversible, for obvious reasons, right? If we send this point back, to r squared, we would get 5, 5. And if we were to try to send the point 5, 5 back into the plane, we would reach back to the same point again. Because what do we do to do that? Well, we'll measure a horizontal distance of 5, and then we'll go up by 5, and hey, we reach the same point again. So the mapping is invertible, right? We go from one point to here, and then here it goes back again. So let's say this is f, this is g. You compose them together, that's the inverse function. So that's the isomorphism between plane and r squared, which they described over here. But since I described, we don't need to go through that again. So it's basically, so this is what we mean by like connecting two different disciplines of math together. We're connecting geometry and, just arithmetic. We can translate the problem from geometry into a problem in arithmetic and vice versa. Because we have the isomorphism, right? We need a way to go from here to here, and we need a way to go, back the other way around. That's why it has to be an isomorphism. It cannot have two different inverses. Alright, let's do this and then we'll wrap up. And maybe I'll do another stream, a gaming one, to just have a break from all the studying. Right, so we have B to A, we have G, and then K. They're both inverses for, it goes from A to B. F. And we need to show that G is equal to K. So I think I already have a strategy for this. So G and K are both inverses. So if we go F and then K, that will be the identity on A. f and then k. And since k is the inverse of f, then this cycling back around is the identity. And similarly, we can go f and then g, f and then g. That's also going to be the identity. So we have k of f equals g of f. Still not, how would you say? Still not what we want, right? We want k is equal to g. This is not exactly that. And what do we do next? I feel like we can just like apply, f inverse on both sides. Or we can like even apply like k on both sides, And and then we can group like this. And we can say what is kf. So we have k and then we have f. So it's going to be the identity on B. And G, fk, fk, also going to be the identity on B. And then we have identity on B and then k. So that's just going to be the same as k. And then we have identity of B and then G. So the identity of B and then G. So that's going to be G as well, and then k equals G. But I think there's another cool way which is worth talking about, and that is this equals 1a. And we know that 1a composed with 1a is equal to 1a. So we can say k composed with f composed with g composed with f is equal to 1a. Right, just here, 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 here. Okay. And I think what we can do is hmm hmm wait, no, I thought this would work, but I don't think so. It requires us to apply like a function on both sides again. Yeah, no, this is just gonna be more complicated than. Hmm. Yeah, this wouldn't work. So yeah, just follow what I did before, and that would be it. right? We have kf equals gf. If we add k on both sides, we could even add g on both sides and it will still work. Like, one important thing, if you're like have like equality and then you want to like apply a function on both sides to see if it works or not, I think is you have to make sure that like everything still makes sense. Because like this makes sense because GFG, you get, you know, G and then F and then G again, right? So let's say if I want to do this and then apply F on both sides, then this will not make sense because we're doing F and then G, but we go from F and then we go F again, like we're stuck here, right? Because F again is going from here back here again. So that doesn't make sense, right? So that's why I don't really like, you know, applying functions on both sides as like a way to explain stuff because there are, you know, problems associated to that, misunderstandings that can occur. But yeah, I think that's really the only way to do it. Really. Oh, maybe one way you can think about it is you have 1A 1A. You can think of it as F1A is equal to F1A, right? So we do 1A first and then F, 1A first and then F, right? And then you can go from here into KF is equal to FGF, and then you can group Jesus Christ, you know what, just forget it. I'm trying to make things more beautiful, but I guess it doesn't work. I guess you could go from this, right? And then you could go like that. So this could be your starting point of the proof. Obviously this is correct, and obviously this is correct because you're just substituting in. And then you group these two and these two together. Okay, what is f of g? Well, f of g is identity. You can see over here. So it's just k identity is equal to g identity. Correct. And then this is just k and this is just g. Correct. So this is the step-by-step way, and this does not require sort of applying function on both sides of the equation. right? Right, because the other way was we go kf is equal to gf, and then we apply g on both sides. Which is also valid, but I don't like it because we have to like check to make sure that we can actually apply the function, because as I gave an example, sometimes that does not work. For example, if you apply f on both sides, that just does not work, right? So you have to, so doing this, going from here to here, this step, you must be careful. However, since we're doing none of that in this step over here, there's no applying function on both sides. It's already done, like, sort of implicitly in like the first step. But like we don't need to check anything here because obviously this is the same thing and this is the same thing and they're obviously equal to each other. Right? So it's just a more elegant, more nice way to like framework things, which I like to do. You know, I like to find the prettiest way to do things that it does not involve any sort of weird complexities that you have to figure out. This is just simple. Wait a minute. Oh, this is GF. This is FG. So this is actually B instead of A. Okay, now it's perfect. Okay. Alright, we're already getting to the slightly harder stuff, but that's fine. That's fine. Alright, I'm gonna stop it for now. Like I said, we'll stop at exercise 2 and we'll continue from there. Let's just see how much left there is to go. Damn, that's a lot. That's a lot to go through before we reach the next session or chapter or whatever. Oh boy, we are getting to the hard stuff. Wow, okay. Ooh, okay, okay. Alright, see you in a few minutes, like 10, 15. I don't know.